one of the things that I've been reflecting on a lot in this sort of modern AI era, I've been studying artificial intelligence and doing research in the area since the 80s. And now it's sort of everywhere, and it makes me want to step back and ask, okay, what is it that we're trying to do again? And what is what we've done so far enable us to do? And I really like to focus in on this issue of, well, at the end of the day, computers are there so that we can give them things to do for us, right? And so how is it that we go about doing that? And how can machine learning actually help with that process? So, I'm sure that, that many of you came here specifically to hear about how to take care of tomato plants. So I'm going to focus in on that for most of the talk. I mean, unless I'm sorely mistaken, but I think that's what you came here for. So I used watering tomato plants or taking care of tomato plants as an example of the sort of thing that it would be maybe useful to delegate to a machine to do on our behalf. But there's lots of other things. There's data analysis questions. There's automatic security protection things. There's all sorts of things that we want to do. But at the end of the day, what we're really focused on is how can we take a task that's in our head and delegate it to the machine. And so we do this all the time from person to person. If a person has some expertise, for example, in taking care of tomato plants, and I maybe don't, then they need to find some way of getting that information into me so that I can carry out the task. I can interact with the environment, take in information, make decisions, and take actions. And so we call that teaching when we're talking about it in the context of people, but we call it programming when we're talking about it in the context of computers. But programming, I'm viewing in a very, take a step back, look at it very broadly. So to set the stage for that, I'd like to show you actually a video I found online that I really, really like on how to take care of tomato plants. So hopefully this will play and you'll be able to hear her. All right, we got no sound. we did practice in advance.
Tomato plant.
Oh, there it is.
The easiest way to determine if it needs watered is the finger test. Simply stick your index finger about an inch down into the soil. If you bring it out and it's dry, it needs watered. When watering a tomato plant, you want to make sure you don't water on top of the foliage, if at all possible. That can cause disease. Always water at the base of the plant, and make sure it's a nice, thorough watering. This plant will love it, as it has great big roots, and they love a nice, deep water.
All right, so again, if nothing else, you can leave this knowing a little bit more about how to take care of tomato plants. But the reason I picked this particular video is it's nice and short, but it really illustrates the four different ways that we have for telling each other what to do, but also how we tell computers what to do. She gave us some explicit instructions in the form of things like stick your index finger about an inch down into the soil. She gave example instructions. So not saying things out loud, not putting things into words, but actually just showing us. One example of that is how she moved the leaves of the tomato plant out of the way. She didn't verbalize that, but you could see her do it with her arm, and that's something that you could now do as well. She gave us some explicit incentives. So in addition to telling us what to do, she also told us what it is that we were trying to do. And that's a really useful thing in conveying a task, because it allows you, as the recipient of the task, to know whether or not you're actually doing it right? As opposed to just blindly following the instructions, you can reflect and you can say, okay, well, the thing I thought I was doing isn't working. I need to change what I'm doing. And she also did example incentives, at least to some degree. She gave us kind of a little facial expression where she was talking about how much the tomato plants love this kind of water. So that's her love face. It doesn't look great in still, but it is. All right. So in the context of delegating tasks like watering tomato plants to computers, we have exactly that same four set of mechanisms that we can use to convey the tasks. The notion of explicit instructions is traditional programming. We actually just write out the steps, right? We have these very sophisticated, interesting ways of doing that, but at the end of the day, we're just giving the computer explicit instructions about what we want it to do. More and more now, we have the ability to actually program computers, tell computers what to do through example instructions. So we actually can take reams, piles and piles and piles of data and train the computer to actually mimic the sorts of things that exist in the data. So that's telling them what to do by example instructions. We don't actually tell them the steps. We just say, this is what it is that you need to accomplish. Just follow these examples. My own research area is reinforcement learning, so that's telling computers what to do through explicit incentives. We actually give it the goal, and then we just let the computer figure out how to act to achieve that goal. And then kind of maybe the least well-known or least studied of these boxes is example incentives, where the idea is, well, it can be really hard to express exactly what I want to have happen, but if you watch my behavior, you might be able to figure out what it is I'm trying to do, and you might be able to do that yourself, we say to the computer. So what I'd like to do in the time that I've got is step through each of the 4 of these and talk a little bit about their strengths and weaknesses and how machine learning is involved. So I'll start with the first one, explicit instructions, or telling the computer what to do. In the context of watering a tomato plant, you might be, you can imagine the sorts of things you might write down. We can take in information, the computer can take in information from the environment in terms of things like how moist the soil is, whether it's a sunny day or not, how tall the tomato plant is, how green the leaves look, so anything that we can actually detect with sensors. And then we can write a program that says things like, well, for example, if it rained today, or I had already sprayed the tomato plant, then or had not sprayed the tomato plant, then maybe I want to give it some water today. Otherwise, maybe I should put off watering the tomato plant today. So this is relatively straightforward. It is kind of the most natural way of telling machines what to do. But one thing that we've learned over the course of the history of programming is actually pretty hard. It's hard for people to get this right. And so one of the examples that means a lot to me, I'm very interested in the question of how these tools can help more novice users actually be able to convey tasks to computers. And so I reflect very often on this research from back in the 1980s, when a researcher told a class, an Ivy League class of undergraduates who were studying programming, Elliot Soloway had those students do a really simple task. So just program the computer to average a list of numbers. Right? Really simple, data analytics sort of thing to do. Very, very natural, very, very basic. But 86% of the students in this class failed. Right? They actually did not write a correct program for averaging the list of numbers. And that was shocking, I think, to people at the time. I think it's still pretty shocking. But the fact of the matter is, it is hard for people to learn to take ideas and take tasks and convey them in explicit enough terms to make them executable. One of the things that we've been doing is, so a thing you might think, a thing that I see on the internet sometimes, like this tweet from Andre Kaparthi, says, well, maybe we don't have to worry about that anymore because the hottest new programming language is English. Right? Now that we have large language models, we can just talk to the computer. And then it's just like, you don't have to learn semicolons and parentheses. You just tell it what to do and it'll do it. So we were like, my students and collaborators and I were like, I think he might have missed the point a little bit. It makes it easier for him and it makes it easier for programmers. But does it actually make it easier for people who don't have that kind of experience? So we did the simplest possible thing. We recruited people off the internet. We asked them to tell another person to basically average a list of numbers. We did a slightly simpler task than that. It was tabulating votes. It was like, so the person we're gonna give your instructions to another person. That person is then gonna have to do this task. Just tell them what to do. And again, we found that about 60% of the people that we recruited couldn't accurately convey that simple task to another person in English, right? Like, this is not magic. This is not code. This is the fact that it's actually really hard to convey a crisp, detailed idea from one place to another, be it to a computer, be it to a person. I think that's actually really instructive and really interesting, right? Like, we can't, even as things become easier for people who are already experts, it doesn't mean that it's actually easier for people who are not experts. So you could say, okay, well, maybe instructions, that was the problem. We should actually focus in on examples. You can do a tremendous amount with examples. You don't have to verbalize it at all. You don't have to put your thoughts into symbols. You just do it, let the computer watch you, and then the computer will be able to do it. And this has been behind, of course, the modern explosion in artificial intelligence. We can handle now speech and vision and language now, and tomato plant watering. You didn't think I was going to let that go, right? So back to tomato plants for a second. How would we use something like supervised learning or example instructions to water tomato plants? Well, it's really simple. We just collect data on Ashley Lemon, which, by the way, great name for somebody who's an expert in tomato plant watering. We collect her choices, right? She was on a particular day with particular inputs. She decided to water the plants, or maybe on a different day she decided not to water the plants. We just collect all this into a giant table. We feed it into the computer. Machine learning algorithms then figure out, okay, how can I be like Ashley, right? How can I water the tomato plants according to whatever implicit instructions she's following? And that is really powerful. It is really remarkable. There's all sorts of problems that we couldn't figure out how to write as programmers that we actually have been able to solve using supervised machine learning. But it has its shortcomings as well. And so if you haven't seen this example, I find it very compelling. So this is a project from 2016 where researchers were training visual recognizer to distinguish wolves from husky dogs, which I thought looked really, really, really similar until I put the two pictures next to each other, and the husky dog is adorable, and the wolf gave me nightmares, right? Like, wolves are, I understand now why there's so many like fairy tales about wolves being the bad guy, because they're very, very scary looking. So they took a bunch of pictures of huskies and wolves, they put them into a classifier, and it learned how to distinguish them. It was something 98% accurate, something like that. It was very, very, very good. Until they showed it a picture like this, where that's a husky dog, but the computer was really convinced that that was a wolf. And so the researchers asked, okay, what in the image, if we mask different parts of the image, when does it stop thinking it's a wolf? And the answer was, well, it's paying attention to the snow in the background. Right? So we showed it lots of examples. It inferred really accurate rules from those examples, but those accurate rules didn't really comport with what we wanted it to know, right? Which is, yes, a lot of wolves are often outside, though I did find a picture of a wolf inside, which was also terrifying. To debug this program, what you have to do is actually take pictures of wolves in your house, right, and make sure that's in the data set so that it can learn to not pay attention to the background. This is an extremely dangerous way to fix a computer program, and so I do not recommend it. All right, so nonetheless, supervised learning has actually turned out to be incredibly powerful, and of course, we're all now living in this weird world where we wanted to write a computer program that was better at predicting what the next word is, given linguistic context. And we didn't know how to write a program by hand to do that, so we decided, okay, let's try supervised learning as a way to do that. And then the system that came out of that was actually remarkably powerful. It could not only be very accurate at predicting the next word, but it could write, and it could translate between languages, and it could have a conversation. It could answer basic questions and solve basic problems, take direction. And weirdest of all, it could write its own programs. Right, from verbal descriptions. It could just turn that into code. So I think that's crazy, right? This is kind of the modern chatbot era that we're in today, and now I guess increasingly, agentic systems built on top of those. And it is really quite remarkable because at root, it really is just trying to do this core task of predicting what the next word is, and then there's all sorts of bells and whistles on top of that. And this has actually been really useful for helping engineers code faster. There are some really deep, hard questions about how effective this is for other people, right? People who are not trained in that kind of sort of technical usage of computers. So I'll say a little bit more about that again, but I wanted to hit the other two boxes in the 2x2 grid. So the next thing to talk about was explicit incentives. And this is the sort of idea that says, okay, we're not going to tell the computer what to do at all. We're just going to tell it what to want, right? What to try to accomplish. And so a program, again, for watering tomato plants, might be as simple as something like this. Repeat forever, use information about the environment, like whether it rained, what the temperature is, the height of the tomato plant, to choose either to spray the water plants or not, with the goal of maximizing tomato plant height. I don't know, I just picked that. Like, probably I want to maximize tomato deliciousness or maybe tomato yield, but like this is something that I can measure pretty directly, and I think it's correlated with tomato plant health. But that's the whole program. It's really interesting, right? We don't have to get into the nitty-gritty of making the decisions ourselves. We don't need access to Ashley Lemon. We don't need to figure out the rules and write them down as code. We just say, this is what we want the computer to do. Go at it. Now, there's a cost to this as well. It is the case that the way that a program would actually learn to do this is by raising lots of tomato plants using different strategies and killing many, many tomato plants, right? Tomato plants will die in the process of actually learning, or the system learning how to be more effective at taking care of them. Eventually, it actually could be better than Ashley Lemon, right? Better than me, better than all of us. But yeah, along the way, it's going to have to do some amount of experimentation to figure that out. And that's not the only problem. That's not the only challenge when we're talking about reinforcement learning. There's, just to point this out for folks who don't know it, computer games has been a great application area for this, but increasingly people are discovering that business analytics is a really, really good match for the sorts of things that reinforcement learning does. So folks, for example, at Amazon are doing supply chain management. A lot of the big tech companies are doing user engagement. If you can measure what it is that you want and you have the ability for the computer to run various kinds of experiments, this can be an incredibly powerful way of creating highly optimized systems. So it's great, but all right, it's not the end of the story, because specifying a goal is hard too. And so I pulled this example again, actually from 2016, where people were starting to really explore this idea at scale. Said, okay, well, let's say that we wanted to write a computer program to play this boat racing game. So what we're going to do is we're going to say, well, the input information that it's got is whatever the pixels on the screen are. The output that it can produce is joystick actions to control the boat as it moves around. And I don't know, it'll maximize score, right? Like games have a built-in notion of objective. Let's just feed that back in as the information that the computer can use to improve its performance. So they did that, and they thought it would be a great boat racer and it would beat all the other players. But this is what it actually did. All right, so this is the boat. It is going around. It is doing something a little weird, maybe at this point, and now it's doing something extremely weird. It's smashing into other things. It's circling an island. It has left the track entirely. It is really no longer involved in the race. It is now going in circles, catching on fire, banging into the pylons, and then it just repeats this as long as time running. And you're like, okay, well, this didn't work. But it turns out it actually did. It's doing what it was told to do. What it figured out is that if you look, there's little green things that pop up. It runs into those. They are all worth points. Just to spice up the game a little bit, the game designers put these little extra things. Once you consume a point, it disappears, but at some point it regenerates. Well, the computer figured out the time that it takes to regenerate and figured out a route that would take it across those little containers over and over and over again, reaping the maximum amount of points per unit time that's possible in this game, but ignoring the actual objective that we wanted, which was to go fast around the track, right? It did this other thing, but that's kind of because it's what we told it to do. So bugs in the context of reinforcement learning can be extremely subtle, right? Really complicated things to deal with because it's just doing what you told it to do. The problem is you told it to do the wrong thing. All right. So the last box I'll kind of hit really briefly, which is this notion of demonstrating intent. So if it's hard to write out in words what objective a reinforcement learner should optimize, maybe we could just demonstrate it. Like, don't do as I say, do as I do. I guess that's the opposite of what we normally say. But like, watch me, watch what I do. Try to figure out what I'm trying to accomplish based on that, and then apply that to actually solve the problem. And there's not as many examples of this, but it is happening. We could do it in the tomato plant world, right, where we figure out what is it that Ashley Lemon is trying to optimize. It's not tomato plant height, but it's probably health, but we don't have a direct way of measuring that. We often use this in the context of robotics to do things like what we call inverse reinforcement learning. So instead of having a program optimize an objective that you give it and create behavior based on that, instead we're actually showing it behavior and asking it to figure out the objective from that. And all these ideas are actually brought together in the context of modern chatbots. So people write code to actually manipulate the data and move it around. People use supervised learning to predict next tokens to try to figure out how language is structured. They infer rewards. They actually refer objectives by having human beings judge interactions, conversations, and then figuring out, okay, what is it that people are rating highly, and what is it they're not rating highly, and then using that inferred information about what people want to try to actually train the system to do better at it. And even that doesn't always work out very, very well, because those inferred rewards can also be gamed. And so a lot of the things that are very frustrating about chatbots have their roots in the fact that we're building them in this way. We're building them using a combination of inverse reinforcement learning and supervised learning and programming. Now, I want to end with just one really, I think, powerful idea, and that is, if you listen to the Ashley Lemon video closely, you notice that not only does she use all these different mechanisms for conveying tasks, but she knits them together. They're all supporting each other. All these bugs, these problems, and the different ways that we have for telling computers what to do, they all kind of have complementary strengths and weaknesses, right? So if when we talk to other people, we tend to use them in concert, and we don't really do that so much on the computer side. Though, we've done some research, my collaborators and I have done some research where we do things like have a system learn to be a home automation system by mimicking your behavior, but then instead of just mimicking it and doing it, it actually then puts that into explicit instructions and then shows it to a person and says, is this the rule that you really want me to follow? All right, so using both the explicit instructions and the example instructions together. And we're looking at other ways of bringing these together. One thing that I think is really kind of surprising is that ChatGPT, these chatbots like ChatGPT, they sort of have naturally learned to do some of this stuff, again, because they're trained on human interactions. So I just wanted to demonstrate that. So I asked ChatGPT, make a list of numbers that aren't prime. I had a particular list in mind, and it generated 1, 4, 6, 8, 9, 10. And that was not the list I actually had in mind. So I said, okay, let me try it by example. That was explicit instructions. Let me try an example. Make a list of numbers like, 4, 6, 8, and so on, which it then came back with the evens, which again is not what I actually wanted. But I combined these two things together. Make a list of numbers that aren't prime, like 4, 6, 8, and so on, and it came back with 4, 6, 8, 9, 12, and so on, like composite numbers other than 1. And so I thought that was actually really neat. And I think we can learn a lot from what's going on inside these chatbots to make programming or to make systems that people interact with that can draw on all these different ways we have of telling people what to do and therefore telling machines what to do. So, all right, so I didn't leave us a lot of time for questions. I really wanted to. I'll just briefly plug my book. If you want to hear more about this stuff, I've got the book Code to Joy. If you want to know more about the history of AI, I actually worked on a book with Eugene Charniak on kind of an intellectual history of AI. But that was it. Let's try to see if we can squeeze in some questions. Thanks.
So does anyone have any gardening questions? Over here. You can step up to the mic if you don't mind. Sorry to make it squeeze out.
I had to apologize to a bunch of people. What's your advice on, I guess, reinforcement learning? I'll give you a real-life example.
Yeah.
So I'm coding, code. I'm fixing a bug. The test stops passing, and I ask it to please make the test pass again. And the first thing it tried to do was to revert my change. It introduced the bug back.
I see.
Do you see the problem, right?
Yeah, of course. Yeah, I mean, so interacting with these chatbots is really interesting, right? Because I think part of it is we don't have a lot of practice conveying things like that, and so I think there's a lot for us to learn as people. But on the other hand, they're not perfect, right? And so it's very often the case that you do what should be the right thing, but it comes back and does something unexpected, right? And I've actually been struggling with that a lot. So yeah, I'm not sure what to tell you. I mean, we need to keep pushing on the companies that are providing these interfaces to us to make sure that they're actually responsive to the modalities that we use when we're actually telling them what to do. But I don't know. I don't think that's a reinforcement learning question per se, though. Do you think? Yeah, just it's
maybe prompt engineering.
Or maybe prompt engineering. But again, I mean, that's one of the things that's really interesting is I started thinking about these topics before chatbots really became a big thing, and it's just so interesting now that we have these alternative mechanisms for actually conveying tasks to the computer that all get filtered through this kind of language bottleneck, and it's exciting, it's interesting, it's different. But it's not the end of the story. I think there's lots of things that we're going to be able to do moving forward. All right, anything else? 50 seconds. Yeah, okay, great. Hi.
Thank you so much for a wonderful talk. I was wondering about the fourth quadrant,
yes,
right, which is definitely the most frontier, weird, out there idea.
Yes. But
I can see lots of potential in it.
Yeah.
Can you speak for a minute to what you've seen work, maybe in the in the working with the kinds of tools that we're using today, and or research that you've seen that's interesting that you think we should be reading so we can move to the frontier too?
Nice. Well, again, so I really do like that last quadrant. I think it's incredibly powerful because it's actually using data to infer tasks or infer objectives, right? Figure out what it is we're actually trying to accomplish. But it has been used to great effect. The loss function learning, for example, there's a lot of work in machine learning where people are focused on the question of like, well, what loss function should I actually ask the system to optimize, given that I know the sort of thing that I want to produce? I just don't know how to translate that into a loss function. So loss function learning is a really powerful way to do that. We actually give it lots of examples of our judgment of what's appropriate and not, and actually can build a loss function from that. But it's a very narrow, noisy channel to convey this information. I think it really has to be combined with the other mechanism. So one thing I skipped over really quickly in the beginning is an aphorism that I found really inspiring when I was thinking about this stuff, which is the mediocre teacher tells, the good teacher demonstrates, the great teacher explains, and the phenomenal teacher inspires, right? And so we're talking about this inspire box. It's like, by my example, you can actually achieve. But if somebody was to teach you just by inspiration, you would learn the wrong thing, right? You have to buttress it with all those other boxes. And so I think that would be my advice, is like definitely think about that box, but think about it in conjunction with the others.